I wanted to quickly go over the two problems on curve sketching that we didn't get a chance to cover in class. Number 2 was y equals 2x minus 3x to the 2/3. Let's follow the steps and see how we can sketch this particular curve. The first thing you want to do is determine the domain of the function. In this case, we're not dividing anywhere by 0. These are perfectly nice power functions. X to the 2/3, sometimes when we're taking a root we have to worry about our input being positive, but in this case, since the root we're looking at is the third root, we are perfectly capable of taking third roots of negative numbers, so in fact y is going to be defined for all real numbers. The next step is to identify the critical points by looking for where the derivative equals 0 or where the derivative is undefined. It's a fairly straightforward derivative, just using the power rule for each of the terms, and we end up with 2 minus 2 divided by the third root of x. So this particular derivative is going to be undefined when x equals 0, because we would be dividing by 0, so that's not allowed. It's a little bit harder to see where this particular function is going to be undefined, or is going to be equal to 0, so just go ahead and set it equal to 0 and solve. Just doing some algebra, you'll end up with x equals 1 as the other location where the first derivative equals 0. This is going to give us two critical points, and while we're at it, let's go ahead and find the points in the function themselves. So when x is 0, compute the output y, you get 0. When x is 1, compute the output by substituting 1 into the original equation, and you get -1. So we end up with 2 points that are going to be on our final graph, 0, 0, and 1, -1. Now we want to go ahead and determine what the candidates for inflection points are. Remember, I call these candidates for inflection points because they are only true inflection points when the second derivative changes sign. So to find the inflection points, we take the second derivative, which means you take the derivative of the first derivative. And as you have seen here, I would recommend using this formulation of the first derivative. It then just becomes an application of the power rule, and you end up with 2 divided by 3 times the third root of x to the 4th. The second derivative is going to be undefined when we're dividing by 0, which is precisely when x equals 0. And in this case, the second derivative is never equal to 0 because there's no way to take the numerator and have it equal to 0, since the numerator is always 2. So there is one candidate for an inflection point, but we won't know for sure until we do our sign analysis. So let's set up the intervals for our sign analysis. We know that 0 and 1 are the x values of interest, so there will be, we need to consider the interval from -infinity to 0, from 0 to 1, and from 1 to infinity. First, we're going to look at the first derivative. Pick your favorite value in between -infinity and 0, and evaluate the function there. Evaluate the first derivative there. So -1 is one of my favorite values. I substitute it into the first derivative, and I see, based on my calculation, that the answer is going to be positive. Between 0 and 1, I might pick a half. That's not going to be easy to do, so let me go over to 1 to infinity. So if I go instead for between 1 and infinity, I chose the value x equals 8 because 8 is something I can take the third root of without pulling my calculator out. And the first derivative at 8 takes on the value 1, which is also positive. Now this is giving me an idea for my middle interval. Rather than trying to find the sign at 0.5, how about if I instead try to find the sign at 1/8? Again, that's going to give me an input that I can evaluate exactly, and I see So based on the sign of the first derivative, since I go from increasing to decreasing, that means 0 is a local max, and then we go from decreasing to increasing, that means 1 is a local min. Let's look at concavity by considering the sign of the second derivative. Checking the same points, in fact we don't even have to check any points at all, because when you take x to the fourth power, regardless of what sign it is, that's going to become positive, so the whole second derivative ends up being positive. That means the concavity never changes, and there are in fact no inflection points. It is always concave up. Putting this together, so for the first section here, we are increasing and concave up. That gives me the right half of a smile. Then we are decreasing and concave down. So that's going to give me the, no, I didn't say that right. We are decreasing and concave up, so that's going to give us the left half of a smile. And again, increasing and concave up gives us the right half of a smile. Again, there are no inflection points because we did not change concavity ever. Before we get to drawing, we want to do an asymptote analysis to see what happens as our function approaches infinity. In this case, because it is a difference, this is an indeterminate form of 0 minus 0. You're going to have to do some algebra. In this case, factor out the greatest common factor, which is going to be x to the 2/3. That will leave you with 2x to the 1/3 minus 3. And when you consider what happens as x grows without bound, x to the 2/3 goes to positive infinity, and 2 times x to the 1/3 minus 3 also goes to positive infinity, albeit a little bit slower, which means the entire function is heading off to positive infinity. A similar analysis as x goes to negative infinity. This time, x to the 2/3 is going to go to positive infinity because of the square that's happening, but the second factor, x to the 1/3, is going to end up going to negative infinity. So positive infinity times negative infinity gives me a negative infinity. With all this information, I believe we are ready to graph the function. Begin by plotting the 2 points we know of interest, 0, 0, and 1, negative 1. We know we start down at negative infinity. We're supposed to increase to 0, 0, decrease to 1, negative 1, and then increase all the way to positive infinity. That means it's going to cross the x-axis somewhere else, and it would be nice if we could figure out what that is. So let's go back to our original function and look for the roots of the function so I can find the other point where we cross the x-axis. So set your original function equal to 0, factor, and so after we've solved this, we find that x equals 27/8, or about 3 3/8, will give us the other place that our function intersects the x-axis. So let's plot that. And now remember, the function is always concave up, increasing, decreasing, increasing, and we can finally draw our function.